Viewers, welcome to our online lesson. Today we shall look at balancing chemical equations for Form 2 chemistry. I am your online teacher, Mr. Steve Gitau, on our channel at Steve Gitau 3660. Viewers, you will find that in Form 2, at times the skill of balancing chemical equations poses a challenge to many learners, and that's why we've taken the task to look at how we balance various chemical equations and what techniques a student is required to have so as to balance these chemical equations very well. One, the students need to know the general chemistry about the equation. For instance, what are the products formed when acids react with metals? What are the products formed when acids react with alkalis or soluble bases? What are the products formed when acids react with metal carbonates? What are the products formed when some metals, for instance, react with oxygen, non-metals react with oxygen, or maybe metals react with some non-metals? You need to know, number one, all the products formed. The second most important thing that a student is required to know is what we had covered in our earlier topic, the valencies of various metals, non-metals, and radicals, and how they are used in writing the chemical formula. So you can always go back to the earlier lesson in case you missed on mastering chemical formulae. Straight away, let us look at some of the various chemical equations that a student is required to master. Number one, a student should be able to know, number one, how to write the equation between a metal and, let us use plus dilute acid. When a metal is reacted with a dilute acid, the products are usually a particular salt plus hydrogen gas, a salt plus hydrogen gas. So with that in mind, then it becomes very easy for us when we shall be looking at these equations. So let's look at number one. An equation between, number one, an equation between sodium metal, and a dilute acid like hydrochloric acid. The salt will be a salt of sodium, and that gives you sodium chloride, and hydrogen gas. Sodium chloride and hydrogen gas. Symbolically, this equation is represented as Na solid, for instance, and HCl aqueous for a dilute acid, and that salt will be sodium chloride, which is soluble, aqueous, that is in solution, and we have hydrogen gas. Now, viewers, it is important to note that there are two atoms of hydrogen on the product side against one atom of hydrogen on the reactant side. So the skill of balancing requires that the number of atoms on both sides, product and reactant, be equal. So we put a 2 before HCl, and that creates two hydrogen atoms and two hydrogen atoms. So hydrogen is balanced. We have created two atoms of chlorine on the reactant side, so we introduce them here on the reactant side. So as far as chlorine is concerned, the atoms of chlorine are balanced. Now, we have two sodium atoms on the product side, and that means we should have similar number on the reactant side. And when we put in a 2 there, you find that that equation is therefore said to be balanced. One thing that we notice here about hydrogen is that it occurs as a diatomic molecule. That is, two atoms occur, they combine, and hydrogen occurs as diatomic. So we do not put hydrogen atoms or two hydrogen atoms. That would be wrong. Let us move on to a second case. Magnesium solid and hydrochloric acid. magnesium and hydrochloric acid. Let's look at that. Number 2, we have magnesium, metal, and hydrochloric acid. Hydrochloric acid. That should give us the products magnesium chloride, and hydrogen gas. Now, let's look at symbolically how that equation is supposed to be. We have magnesium being shown as capital M and small letter G, and HCl, the hydrogen being capital. This is aqueous. So the product will be magnesium chloride, aqueous. The chloride of magnesium is soluble, and hydrogen gas. Once more, the hydrogen is diatomic. Now, we have 2 atoms of hydrogen here against 1. So we put a 2 here, and that balances the 2 hydrogens, and automatically 2 chlorines, 2 chlorine. The magnesium atom is 1 here and 1 here. That creates a balanced chemical formula for that. Number 3, let's look at the case of aluminium. Number 3, we have aluminium solid reacting with some dilute hydrochloric acid, and this gives us the compound product aluminium chloride, and hydrogen gas. Aluminium chloride and some hydrogen gas. Let's look at how we balance on such. You find that this symbolically, aluminium is Al. The L is a single letter. We do not write aluminium as so. That is wrong. Right, so we have it in solid form plus HCl aqueous, and that gives us aluminium chloride and hydrogen gas. Now, viewers, as we had hinted earlier, the knowledge of valencies. You find that the valency of aluminium is 3. So we bring down this 3. The valency of chlorine is a 1. So we bring that 1 here. Now let's come to the balancing. We have introduced 3 chloride ions on this side. So even if we are going to slowly be deleting, balancing can be done for starters using a pencil so that you can rub off as you change. So I'm going to use my erasable pen here and create 3 hydrogen HCl molecules. This will take care of the 3 chlorines. However, if you look at the hydrogens here, there are 3, and on this side there are 2. So we need a common factor. In mathematics we say LCM. A common multiple of 2 and 3, and that happens to be 6. So how do we create 6 chloride atoms here? We can multiply that by 2, so that 2 by 3 is 6. And I delete this 3, my earlier 3, and I now put in 6. So that we have 6 chloride atoms and 6 chloride atoms. 2 times 3 it gives you a 6. At the same point, you realize that there will be 6 atoms of hydrogen here. We need 6 atoms of hydrogen on the product side. That is easy. We multiply 3 by 2 to make a total of 6. Now, what is now left is to ensure that the aluminium atoms are balanced. 2 here, and therefore we have a 2 here. And that way, the equation can be said to be balanced. In the activity that is going to follow, I would like us to do an activity, and this time round, we are not going to write the word equations. In Form 2, we now have graduated. We shall write the symbolic equations only. So I will delete this material. I will delete this material so that we can use the same space and now write chemical formula without putting the word equation. We shall only use the symbolic equation in form of an activity. So I'm going to give you some time, 1 minute or 2 minutes. I'll pause so that I'll allow you to balance the equation yourself. So we look at activity 1. In our activity 1, I would like you to balance the following equations. Number 1, the reaction of magnesium solid with dilute nitric acid. Dilute nitric acid, that is HNO3, and it's soluble in solution form. What do we get? Number 2, the equation of zinc solid and dilute sulfuric acid, H2SO4, aqueous. What do we get? And number 3, I would like you to attempt and balance the reaction between potassium and dilute sulfuric acid, H2SO4, aqueous. So viewers, take 1 or 2 minutes to complete, and then we balance the equations in a few minutes. Viewers, welcome back. Now, with that, I believe you have had time to look at the equations, and normally we say when a metal reacts with an acid, we develop a salt and hydrogen gas. And our salt here is magnesium nitrate, aqueous plus hydrogen gas. So the comment that we had done earlier, that the knowledge of valencies is very important. Magnesium nitrate goes by that formula. Since the valency of magnesium is a 2, and we bring it here, the nitrate radical has a valency of 1. Now, coming to the balancing, it means we have 2 nitrate radicals here. On the reactant side, it is 1. So we balance that with a 2. That creates 2 hydrogen atoms and 2 hydrogen atoms here. So the hydrogens are balanced. The magnesium, we need 1 atom here, and we have 1. So for that part, the equation is said to be balanced. Let's come to equation number 2. The product will be zinc sulfate, which is soluble, and there will be some hydrogen gas. Now, when we have the formula for zinc sulfate in this form because the valency of a sulfate is a 2, and zinc is a 2. So it is self-balancing. We have 2 hydrogen atoms on the product side and 2 on the reactant side. 1 zinc on the reactant side, 1 zinc on the product side. So the equation is self-balancing. Number 3, the product will be potassium sulfate, which is soluble together with production of hydrogen gas. Now, the requirement here, we have 2 potassium atoms, and here we need to put 2. The sulfate is 1, hydrogens are 2, so with that the equation is balanced. So viewers, that marks part 1 of the kind of equations that we have that require balancing. We move on with part 2. In part 2, we look at the reactions of dilute acids and alkalis, or what we call soluble bases. So that is going to be our second subtopic here. So let's move on. In part 2, we are talking about dilute, the reactions of dilute, number 2, dilute acids and dilute bases, or what we call alkalis. Alkalis are bases that are soluble. For example, let's take one. This is a series of equations which are quite familiar. We may not take so long in this one. Number A. Take, for example, when we have a dilute acid, hydrochloric acid, reacting with a soluble base, sodium hydroxide. And what do we get? We get, normally, when these two react, we are able to form a particular salt and water as the products. So we shall be looking forward to getting a product which is a particular salt. The salt formed here will be the reaction between these two, and that forms sodium chloride, which is soluble. And then we have the hydrogen react with the OH, and the two react to form water. The two react to form water, liquid. We count on the number of hydrogens. Let's start from this end. 1, 2. We have 2 hydrogens. Hydrogens are balanced. Chlorine is 1, 1, balanced. Sodium is 1, 1, balanced. And the oxygen is 1, and here we have 1. So that equation is balanced. Number B, let's look at the case of nitric acid. Nitric acid, which is soluble, reacting with magnesium hydroxide. Magnesium hydroxide. We take it as soluble here. Now, you find that the product, as we had said here, will be the salt. Which salt is here? We have the nitrate reacting with magnesium to form magnesium nitrate. Magnesium nitrate. Magnesium nitrate with a 2, and that is soluble. All nitrates are soluble, and the production of water. Let's count. We have 2 nitrate radicals, and here we have 1. So that means we need to balance with a 2 here. And the nitrates are balanced. Let's look at the case of others. Magnesium, we have 1, 1. The hydrogens are 2 plus these 2, and that makes 4. So we need to put a 2 here, and that case gives us 4 hydrogens. What about the oxygens? On the product side, we have 2. Here on the reactant side, we have 2. I have not taken time to count on the nitrate because wholesomely, the 2 nitrates were taken away by the magnesium. Number 3, we look at sulfuric acid reacting with sodium hydroxide. Number C, sulfuric acid reacting with sodium hydroxide, for example. What do you get? We get the salt, sodium sulfate. Sodium sulfate. Viewers, it is important we master valency because the valency of a sulfate is a 2, so we bring that 2 here. A sodium ion or sodium atom has a valency of 1. So that is the correct formula of sodium sulfate, and that goes together with the water liquid. So we balance. What do we get? The sodiums are 2, so we introduce a 2 here. The hydrogens are now 2 plus these 2. That makes 4. How many do we have here? 2. So we balance that by placing a 2. Look at the others. The sulfate is 1 here, and we have 1 here. The oxygen are 2 here, and we have 2 times 1, that makes 2, and that equation is also balanced. The last one is going to involve HCl and calcium hydroxide. Number D, we have hydrochloric acid, HCl, and calcium hydroxide. Calcium hydroxide. Let's take it to be soluble, slightly soluble there. And what do we get? We get a salt of calcium, which is calcium chloride. So I would like you to master the way you put calcium chloride and water, and that gives us liquid. Now we move on and balance. We have 2 chlorines, so we need to have 2 chlorines here, 2 hydrogens here, plus these 2, that makes 4, and these ones, therefore we need 2 here. The oxygens are 2, and here they are 2. Calcium is 1 here, 1 here, and that equation, viewers, is balanced. So viewers, we are going to the third section. We take a short break, and when we resume, we shall be looking at the reaction of metals, with oxygen. Let's see you in a short while. Viewers, welcome back. We look at reaction of metals with oxygen, just a few metals and their reaction with oxygen. Take, for example, number 1. How does sodium react with oxygen? Number 1, the reaction of sodium and oxygen gas. Here, I have put this example to make it very clear that sodium oxide is not written in this form. Sometimes you find students making this mistake. They have ignored the concept of valency. The valency of oxygen is a 2, and we should be able to bring it at that level. The valency of sodium is a 1. So this is a correct formula of sodium oxide. Now, how is the balancing therefore? And sodium oxide will occur as a solid. So how is the balancing? We have 2 atoms of sodium, yet here we have 1. So we introduce a 2. And that takes care of the sodium. 2 here, 2 here. However, if you look at oxygen, which we said is a gas and occurs as diatomic, you'll find that we have 1 and here they are 2. So we move on and balance the oxygen by putting a 2. Now we have 2 oxygens, but we have changed on the number of sodium atoms. They are now 4. So it is good we change on the reactant side, and here we make it 4. So 4 sodium atoms and 4 sodium atoms balances 2 oxygens, and the 2 oxygens, the equation is therefore balanced. So it is important that that skill of balancing coupled with the skill of valency comes up together. Number 2, let's look at calcium and oxygen. So we have calcium in number 2. Calcium, when reacted with oxygen, what do we get? We get calcium oxide. The formula for calcium oxide is CaO. The valency of oxygen is a 2, and that is a 2. Let me put it here. We have calcium valency 2, oxygen valency 2. Upon closing, we get calcium 2, oxygen 2. We normally say divide by the common denominator here, and that takes or gives us calcium oxide as the correct formula. So when we put it like that, it is quite correct. Now, let's move on to the balancing aspect of it. You find that we have 2 oxygen atoms, and here we have 1. So we balance with the 2 here. That takes care of the oxygens. 2 calcium atoms, and here we have 1. So we introduce a 2, and that balances that particular formula. Let's move on to magnesium and oxygen. Number 3, we have magnesium, that is magnesium solid and oxygen gas. So we get when magnesium burns in oxygen, we get the brilliant white frame or white light with a white solid being left behind. So that is what we are having here. Magnesium combines with oxygen in an ionic bond, and that one is formed. We balance that once more. Two oxygen atoms require two atoms here, so we put a 2 and we have a 2 here. Now, viewers, we need to move on and get others in form of an activity which I would like us to do it together. In your notebook, let's look at the activity of activity 2. Activity 2. Activity 2. Number 4. Write balance equation involving aluminium when it reacts with oxygen gas. When aluminium reacts with oxygen gas, what is formed? Number 5. What is formed when iron, and I want to specify here, is iron with valency 2 that reacts with oxygen gas? What is formed? And part 6, we have this other valency of iron, which is iron 3. When iron 3 reacts with oxygen, what is formed? So take 1 minute to answer on this. We can pause on the video and work out this activity, because I would like this lesson to be as interactive as possible. So take 1 minute, pause on the video, work on it, and soon I'm going to provide the answers in the program. Viewers, welcome back. I want to believe that you have worked on the activity, and we can now proceed. When aluminium reacts with oxygen, we get a compound aluminium oxide with the formula Al2O3, and it is in solid form. Now, if you look at this, we are required, therefore, to have 3 oxygen atoms, yet here we have 2 of them. So this is where we come back and agree what is the common multiple between 2 and 3, and that happens to be 6. So on either side, we create 6 atoms. How do we create 3 on this side? Is by multiplying by a 2. 2 times 3 totals 6 atoms of oxygen. And how do we create 6? Is by multiplying by 3. 3 times 2 makes 6. So the oxygen is balanced. Now, if you look at the aluminium, we have created 4 atoms. So we bring in 4 here, and that balances the equation quite well. Let's look at this one. The fact that we are strictly told the iron is iron 2 means that we shall have to create the formula for iron 2 oxide that way. The 2 comes here, and we cancel out the common denominators. So iron 2 oxide goes by that formula. Then we do the balancing. 2, let me use black. 2 atoms of iron. So we have 2 atoms of oxygen. We bring in a 2 and 2. The iron are 2 atoms, so we bring in 2. So 2 atoms of iron, 2 atoms of iron, 2 of oxygen, and that's balanced. What about iron 3 oxide? So we have iron and the oxygen. The valency of oxygen is a 2. That of iron 3, we bring the 3 down here, and that creates iron 3 oxide. Once more, we need to strike a balance. 3 atoms and 2. So we bring in 3 here and 2 here. That makes 6 atoms of oxygen, and here 2 times 3 makes 6. These are 4 atoms of iron, and we get 4 here, and the equation is balanced with the proper state symbols. And that way we shall be able to have that activity done and the reaction of metals and oxygen. Straight away, we move on to part 4, whereby we shall look at how dilute acids react with carbonates. This is a section which we met in Form 1, part of it in Form 1, and it still occurs in Form 2 chemistry. That is the reaction of dilute acids with carbonates. Number 4, reaction of dilute acids and metal carbonates. Now, this is very interesting because we form 3 products. The first one being, we can put it here, salt, some carbon 4 oxide, carbon 4 oxide gas, and water. 3 products are evolved. Straight away, let's look at number 1. Take, for example, a dilute acid like nitric acid. Nitric acid reacting with a very common carbonate, metal carbonate, sodium carbonate in solid form. We generate the salt. The salt will definitely be a salt of sodium. So we find that salt is going to be formed after sodium takes on the nitrate, and that gives us sodium nitrate, which is soluble. All nitrates are soluble. And the hydrogen here, being the representative of the acid, attacks the carbonate to remove one oxygen, and the carbonate is left as CO2, carbon 4 oxide. That one oxygen which is removed combines with the hydrogen to form water in liquid form. So as we have been doing in an equation like this one, chemical equation, the state symbols must be shown. And then the second most important part is the balancing. We balance by counting on the atoms on the reactant side. They should balance on the reactant side. So here we have 2 sodium atoms, and here we have 1. So we put a 2 here. I remember a student may ask, why don't we put the 2 here? That will mess with the valency of a nitrate. It is not 2. So the 2 comes here. 2 sodium atoms, 2 sodium atoms. Let's look at the nitrate. We have created 2 nitrates here, so we need to introduce 2 here. The nitrates are balanced. The hydrogen atoms are 2 there and are 2 here. The carbon is 1, and we can do a sum total of the oxygens. This is 1 plus 2, those are 3, plus 6. That makes 9. If we sum these ones, we have 3 plus the 6, that makes 9. So that equation at this level is balanced. Let's look at another one. We have HCl and magnesium carbonate. Number 2, HCl aqueous and magnesium carbonate. Sorry. So what are the products? The salt, magnesium chloride, going by that formula, is soluble. We have carbon 4 oxide, gas, and water, liquid. So we need to check on the numbers of atoms in each case. We have 2 chloride atoms. Here we have 1. So we put a 2 here. Creates 2 hydrogen atoms. We check. We have 2 of them here. We check on the oxygens. This one's 3, 2 plus 1, and that is balanced. Number 3. Let us take, for example, sulfuric acid and potassium carbonate. Sulfuric acid sulfuric acid, number 3, and potassium carbonate, which is in solid form. So the metal potassium takes on the sulfate, and we get potassium sulfate as our salt, aqueous, soluble. All potassium salts are soluble. And then we have CO2 gas plus water. And then we check on the balancing. In this case, the sulfate is 1, and here we have 1, 2 potassium, 2 potassium, 2 hydrogens, 2 hydrogens. The oxygens are 3. We have 2 plus 1, that is 3, 1 carbon and 1 carbon. So that equation is self-balancing. Let's look at the last one. Nitric acid and zinc carbonate. Nitric acid and zinc carbonate. That is number 4. Nitric acid, aqueous, and zinc carbonate. Zinc carbonate, that is in solid form. You find that the salt formed will be between zinc and the nitrate. So the formula for zinc nitrate goes by that formula. And all nitrates are soluble, so aqueous plus CO2 gas plus water liquid. Now, let's look at the balancing. We have 2 nitrates here against 1. So we introduce a 2 to give us 2 nitrate, 2 nitrate. Then we have 2 hydrogens, and they are here. 1 carbon, 1 carbon. The oxygens are 3, 2 plus 1, and that is balancing. So viewers, that is the part on how you can balance equations that require the reaction between dilute acids and the respective carbonates. Finally, I would like us to look at the reaction between metals and some non-metals. The reaction between metals and some non-metals. Because that is an area which we study in Form 2. In Form 2, that one is very well discussed under various topics. It is not that we shall study this balancing as a topic, a full topic. No, the skill of balancing equations will be inculcated slowly by slowly. In every time you talk about a reaction, always viewers attempt to write it in such a way that you can convert the word equation to symbolic equation so that you are able to get it right. So straight away, let's look at the 5th one, and this is the reaction of metals with some non-metals. Number 5, the reaction of metals and non-metals. Not all non-metals do react, but we shall focus our attention on the reactive ones. Take, for example, a simple case of magnesium reacting with chlorine. Roman 1, magnesium reacting with the chlorine gas. This is magnesium solid. This is a reaction which is quite exothermic. You find we form the product magnesium chloride, and that is in solid form. And it is self-balancing. Let's talk about aluminium and chlorine. Number 2, aluminium solid and chlorine gas. We form the product aluminium chloride solid. So here we are required to do the balancing. Like we had done earlier, we count on the atoms. There are 3 atoms of oxygen here. There are 2. What's the common multiple? We have a 6. So we can introduce a 2 here, so that 2 by 3 is 6 atoms of chlorine. And here we introduce a 3, so that 3 times 2, we get 6 atoms of chlorine, and the chlorines are balanced. So we are now left with the aluminium. There are 2 here, and yet you have 1. So we introduce a 2 here, so that the aluminiums are balanced. We need to look at other examples of chemistry equations that we have met across in our studies. Look at the example on how halogens, indeed chlorine is a halogen, react with a metal like iron. What happens when iron, that is our example number 3, iron reacts with chlorine gas? Viewers, it is important to note that we do not form iron 2 chloride. Instead, iron 3 chloride is formed. The reason being that chlorine is a very strong oxidizing agent. The moment iron 2 chloride is formed, chlorine oxidizes it further to iron 3 chloride by removing an electron from the iron 2, making it iron 3. So we form iron 3 chloride solid. So this requires balancing. We have 3 chloride atoms. So the common multiple between 3 and this 2 is a 6. 2 times 3 makes 6. So we have a 3 here, and that creates 6. 3 by 2 to make 6. The iron are 2, and that creates 2 here, and we have 2 iron atoms. We look at another one, the reaction between iron and bromine. Number 4, the reaction between iron, usually we react the iron in form of iron filings, iron and bromine gas. You find we have iron 3 bromide. With the same reasoning, bromine and chlorine are such strong oxidizing agents, they form the iron 3 compounds of each. However, iodine, even if it is amongst the halogens, iodine forms iron 2 iodide. It does not have that strong oxidizing power to form iron 3 iodide. Instead, we are saying iron 2 iodide is formed. So we balance that as above. We put in a 2, this is in solid form. We put a 3, and this we put a 2. Now, 2 more equations that we encountered, and this one are the reaction of alkaline earth metals with nitrogen, specifically magnesium. So number 5, magnesium. How does magnesium solid react with the nitrogen gas? You find that we form a compound called magnesium nitride. Magnesium nitride. How is the formula? The valence of magnesium is a 2, so we bring it down here. That of nitrate is a 3. So that is the formula for this compound we are calling magnesium nitride. Magnesium nitride. IDE, magnesium nitride. Now we balance that. 3 magnesium atoms creates 3 here. Nitrogens are 2, and they are balanced, so that equation is okay. In a similar way, we have calcium reacting with nitrogen. That is Roman 6. Calcium solid reacts with the nitrogen gas to form this compound calcium nitride. So that is calcium nitride with a 2, and the calcium is 3. So there are 3 atoms of calcium, and that creates 3 here, and 2 nitrate atoms, 2 of them here. The nitrogen are 2, and here they are 2. We have it in solid form and in solid form, and that way, as we are saying, this is calcium nitride. So viewers, this is just one lesson that takes us through the works of Form 2 chemistry in terms of balancing chemical equations. Remember, we shall not stop at this one, because there will be more equations in Form 3 involving our compounds of carbon, involving organic chemistry, and further chemistry in Form 4, whereby the skill that you have learned will also be used there. And we are, in summary, we are saying the student must master the valency, the chemical formula the correct way, and then the ability to count reactants on number of atoms on the reactant side and number of atoms on the product side. With that, viewers, we come to the end of our online lesson, and mine is to urge you where you feel you have a challenge with the balancing of any equation, post it on the comment section and I'll be able to reply. Thank you so much for watching, and coming up next, we shall be looking at calculating relative atomic masses. This is going to be quite interesting in the sense that students sometimes have a challenge whenever they are asked to do a reverse question whereby they are being given the RAM and the percentage abundance is not given. Those are the kind of questions that we shall have in our next video on calculating RAM. Once more, thank you. Subscribe, share, comment, and we shall grow the channel. Thank you.